ESA's mission, LISA Pathfinder, will take us one step closer to being able to directly check the arguably most famous scientific theory posed, Albert Einstein's theory of general relativity. One of the predictions of this theory are gravitational waves, the universe's mechanism for transmitting information about the weakest of the fundamental forces, gravity. LISA Pathfinder will test the extremely precise technology required to measure gravitational waves, and thereby is the first step in opening a new window into the gravitational universe. So much of the science and technology around us today is based on how gravity, the fundamental force of our universe, works. But the gravitational waves of Einstein's theory have never been directly detected. What makes these detections so difficult is that the effect of the passage of a gravitational wave is so subtle that it requires an incredibly large and sensitive detector to measure it.
The general theory of relativity predicts what we expect to see from gravitational waves in terms of the ripples in space-time. And for a very large signal, that would be two galaxies merging, the supermassive black hole, the centre of a galaxy is really crashing together, and then we have to measure picometers, changes in the arm. 1 picometer being roughly 1/100th the size of an atom. This is very difficult, and it's not believed that it's even possible.
These measurements are only possible with a very large detector like the one here, called GEO 600. It has two 600-meter-long laser arms housed in vacuum tubes that run at right angles to each other along fields just south of Hanover, Germany. A gravitational wave of sufficient amplitude would make the two beams go out of phase by a tiny but measurable amount. By recording this phase change, scientists can determine the properties of the gravitation wave signature and hence the astrophysics of the celestial body which produced the waves. However, so far gravitational waves have not been directly detected.
So far we haven't found anything, but any minute now a star could explode and then we would see a signal.
The difficulty of measuring gravitational waves from ground-based detectors is that major astronomical events, which are observable from Earth, are rare, and when they do happen, the distortion created by the Earth itself can mask the signal. This has driven the desire for a lower frequency space-based detector where the signals are plentiful and the detector is free from Earth-induced noise.
Gravitational waves are ripples in the fabric of space-time. And in order to measure these ripples, we have to build detectors which are only susceptible to the gravity of space. So we have to remove all the other forces like thermal forces, solar radiation pressure, magnetic forces.
So LISA Pathfinder will be sent to a stable orbit 1.5 million kilometers from Earth towards the Sun, known as the first Sun-Earth Lagrange point. However, another problem is how to avoid distortion to the measurements of this incredibly precise but sensitive detector from the engine and workings of the spacecraft itself.
Now, the spacecraft itself has a bigger effect than what we're trying to measure. So the real challenge of gravitational wave measurements and LISA Pathfinder are how to build a spacecraft which isolates the test mass from everything else.
The test masses in the case of LISA Pathfinder are two solid gold platinum cubes that float in near-perfect gravitational freefall, enveloped and protected within the heart of the spacecraft, their tiniest movements being measured and relayed back to us here on Earth. LISA Pathfinder is a pure technological experiment to show whether it's possible to create a detector in space of such sensitivity and accuracy that it can measure these waves that are passing through us all the time without us consciously noticing them. After the successful demonstration of the technology, ESA plans a much bigger mission involving 3 spacecraft flying in formation linked by lasers.
After we do LISA Pathfinder, we then take effectively 2 or 3 LISA Pathfinder spacecraft. We separate them by 5 million kilometers. We have 1 cube in each spacecraft and we measure the distance between the cubes. So the LISA Pathfinder mission was instigated by ESA to actually test if we can ever make the measurement. And as of today, we believe we can do that.
LISA Pathfinder isn't just about proving Einstein's theory 100 years after it was first proposed, but the very precise technology developed for this mission and the ability to detect gravitational waves can potentially open up a new and yet unobserved dimension of our universe.